Hello, my name is Nicole Martin. I am in section M05, and this is my Lab 5, Motion of Falling Objects. The objective for this lab was to observe the motion of two objects that are dropped from rest. One object had to be falling quickly, and the other object had to fall slowly. So, the object I chose to represent an object falling quickly was a baseball. So my calibration stick was set to the diameter of the baseball, which was 0.073 meters. My axis is oriented, the origin of the axis is oriented at the middle of the baseball. Our x-axis is oriented in the positive x direction, and the y-axis is oriented in the negative y direction, so that the position of the ball would be graphed in the negative y direction. So the duration of this clip is about 0.5 seconds. And so as you see the ball traveling, so we see that the ball traveled about this distance in that amount of time. So when we model this in Python, here we have the mass of the ball, which is 0.149 kilograms, and the duration of the time that the ball fell, which is 0.583 seconds. Our variable for gravity is equal to 9.81, and here we have our force of gravity, which is the mass of the ball times negative g, since the ball is falling towards the earth and in the negative y direction. Here our coefficient of drag is 0.5, and the force of drag is equal to the coefficient of drag times the magnitude of the ball's velocity. Next we have the net force, which is the force of gravity and the force of drag acting on the ball. And next we have Newton's second law. So when we run this, that's what we get. And graphing these two, we see that our Python model was a really good representation of our tracker data. But now let's consider if there was no drag acting on the ball. We now see that our Python model isn't a good representation of the data we got from tracker. And if we compare these two, like, it's clear to see that this model right here is a much better representation than this model. So now let us consider our slow falling object, which I use as a sheet of paper. The axis is has the origin at the middle of the paper. The calibration stick is set to 0.279 meters, which is the length of the paper measured diagonally. The axis is still oriented in the same direction, with the x-axis going this way. The negative y-axis is going this way, so that the position of the ball is graphed in the negative y-axis. The duration of this clip lasts about 2.4 seconds. And something I forgot to mention earlier, the frame rate for each video I used was about 12 seconds. So now when we model this in Python, we see here the mass of our sheet of paper, which is 0.012 kilograms. The duration of the time of this clip is 2.4 seconds. Gravity stays the same. Again, force of gravity stays the same. The coefficient of drag that I used here was 0.3. Our force of drag vector stays the same. Our net force equation stays the same, and so does Newton's second law. So when we run this, that's what we get. And we see this right here. So once again, using drag and gravity, our Python model is a very good representation of our tracker model. Now, if we were to just consider gravity, our models are going to be completely different. So see, these graphs don't even match up like at all. And when comparing the two, we can see that when we consider drag and gravity, it's a much better representation than just considering gravity only. So, what does this mean? Which model predicts terminal velocity? In my opinion, I think that both graphs show terminal velocity, especially when we're considering the slow falling object, because the graph that dealt with gravity only, it went from like a curve to like this like straight line, so that showed that the velocity became constant, and the other graph was a straight line the entire time, so it had a constant velocity. And our last part of this video is like, what if the slow falling object had been thrown? This video shows a sheet of paper being thrown down, and when we look at this model, we see that this excuse me, this information from tracker, I believe, also does reach a terminal velocity. So going over our tracked motion of each object, we see that when modeling these motions, that you have to consider all the forces acting on the object to get a good representation of what actually happens. Thank you.